post this recording to the YouTube channel. All right, properties of amines. So the nitrogen in an amine is sp3 hybridized. This goes all the way back to the beginning of organic chemistry 1, even in your general chemistry days when you would have discussed hybridization. So you need to know the hybridization of that nitrogen atom. What else? We see the bond angles around the nitrogen are around 108 degrees. So if you measure this bond angle here, it's around 108 degrees, which is smaller or lesser than the typical 109.5. Why is that? The 109.5 degrees. It's because of the repulsion of this lone pair that pushes those alkyl groups down and brings them a little closer together. So it tightens that bond angle somewhat. Then in terms of the bond lengths, if you look at the carbon-nitrogen bond length, we see that it's about 147 picometers, which is a little shorter than a carbon-carbon bond, but it's a little longer than a carbon-oxygen bond. And that makes sense because if you think about as you go across the periodic table from boron to carbon to nitrogen to oxygen, that the size of the atoms gets smaller based on the effective nuclear charge. And anyhow, it says here, under what circumstances would the nitrogen be sp2 hybridized? And the answer to that question is we have sp2 hybridization in an amide. And this is something that we covered in either the first or the second chapter of organic chemistry 1. So we'll put here an amide is where that would happen. If you just look at the lone pair on the nitrogen here, and then you've got 3 bonds, you might think that it is sp3 hybridized, but in fact it isn't, and it's because these electrons are delocalized. We're going to talk about that more in a little bit, but make sure you're aware of that as well. Well, let's move on from there. And if we think about the chirality of an amine, well, if you have an amine that has 3 different alkyl groups, let's say you have a nitrogen and it's got R1, R2, R3. All 3 of them are different. You've got 4 different groups. You've got 3 different R groups and a lone pair. That would mean that the nitrogen atom is chiral. However, amines are generally not optically active. That means that they don't rotate plane polarized light. Well, why would that be? It's because they can invert themselves so rapidly, and it takes very little energy to do that. The pyramidal conversion occurs very rapidly at room temperature. It's only got an activation energy of 25 kilojoules per mole. And so we go from one chiral nitrogen, and then it flips to the other chiral nitrogen. So you create, essentially, you invert the stereocenter. And when it does that, since it can happen so rapidly at room temperature, it leads to amines not being optically active. And we definitely can't resolve, we can't resolve amines at room temperature. I mentioned hydrogen bonding earlier on, and that's something that you need to be fully aware of. And it says here that generally speaking, amines with fewer than 5 carbons are going to be soluble in water. Primary and secondary amines can intermolecularly hydrogen bond and have higher boiling points than tertiary amines. So let's take a look at both of these figures here. If you look at the top row of compounds, we go from propane, which is an alkane, then we go to ethylamine, which is an amine, and then we go to ethanol, which is an alcohol. And you see what happens is that the boiling points increase dramatically as we go from the alkane, which possesses no opportunities for hydrogen bonding, only London force is there. Then we go to the amine, which can experience hydrogen bonding because we have 2 nitrogen-hydrogen bonds. But then we go to the alcohol, which has a much higher boiling point. The reason why the boiling point of the alcohol is so much higher than that of the amine is that even though we have the partial negative and the partial positive charge in an amine that allows the hydrogen bond to occur, it's much greater in an alcohol, much, much greater. Why? Because oxygen is much more electronegative than nitrogen. And so the hydrogen bonds are much stronger in an alcohol than they are in an amine. If you look at the amines on the bottom, we have propylamine, which is a primary amine, ethylmethylamine, which is a secondary amine, and trimethylamine, which is a tertiary amine. All of these compounds are constitutional isomers of one another, but you see that the boiling point decreases as we go from the primary to the secondary to the tertiary. Well, hopefully you can see that the tertiary has no opportunities for hydrogen bonding. There's a nitrogen in the molecule, but there's no nitrogen-hydrogen bond in there. However, if we compare the primary and secondary amine, what we see is that the primary amine has 2 nitrogen-hydrogen bonds, whereas the secondary only has 1 nitrogen-hydrogen bond, and thus the propylamine has more potential for hydrogen bonding, and that's why it has a higher boiling point. So make sure you're aware of both of these trends in here, and make sure that you're also aware of this rule at the top that generally speaking, with less than 5 carbons, it's going to be soluble in water. Like I told you before we even started this chapter, many small molar mass amines have unpleasant odors. You can even see the names here. Putrescine, you know, you've heard of the word putrid, and everybody knows what a cadaver is. So cadaverine and putrescine, these both have the odor of rotten fish. So they don't smell very good. And something that I brought up with you before the lecture started today was fish odor syndrome, which is where the body is unable to oxidize that trimethylamine that we saw on the previous slide. Now, something that we don't talk about on, or something that we don't really talk about in this class are what are called N-oxides. It's a functional group we don't discuss. It's where you have a nitrogen with 4 bonds. You have an oxygen with a negative charge. Like this is called an N-oxide. And people that have that fish odor syndrome, what they lack is the flavin-containing monooxygenase that enables the oxidation to this N-oxide, which is odorless. So this is odorless, whereas the trimethylamine smells terrible. Anyhow, just something kind of interesting there. So the trimethylamine can build up in the sweat, in the urine, and the breath, and yeah, it has some pretty horrible side effects, I would say. Well, let's talk about the basicity of amines, because we talked about how an amine is an organic base. It's not a strong base like sodium hydroxide and lithium hydroxide. However, amines are basic. Take a look at this reaction here. If you look at triethylamine, remember what I called this TEA earlier on? Well, triethylamine can actually rip a proton off of acetic acid to form this triethylammonium ion. So you'd call this triethylammonium ion, and the acetate ion. So this is the acetate ion over here. That's just a conjugate base of acetic acid. And I guess I better label them all now. This is acetic acid. Well, if we look at the acid and the conjugate acid, the pK of the acid, acetic acid, is 4.76, whereas the pK of the conjugate acid is 10.76. Remember, the equilibrium is going to lie to the side of the weaker acid. And that is why triethylamine can quite effectively deprotonate acetic acid. It's also a very good idea to have a general idea of the pKa values of protonated amines. Now, our book goes into quite a bit of detail in this table here, but the reason why they put this table in our textbook is because the basicity or the basicity of an amine can be quantified by looking at the pKa of the corresponding ammonium ion. So we never look at the pKa's of bases, or very rarely. I know we do. We looked at the pK of ammonia and things like that a little bit here and there. But when we're talking about the basicity of all of these amines, it's much easier to actually look at the pK of the ammonium ion, because what do we know? The higher the pKa of the conjugate acid, it means that it's a weaker acid, and that means it's a stronger base. So if I was to compare, let's say, the pK of this ammonium ion and the pK of this ammonium ion, you see that there's 1 log unit approximately of difference. Well, if this is a weaker acid, it means that diethylamine must be a stronger base than trimethylamine, which must be a weaker base. So that's kind of the rationale that I'm going to take moving forward when I'm talking about base strength. Which one of these amines is the strongest base? Well, we're going to look for the lower pKa. Stronger All right. So let's just scribble this out here. And let's move on to here. So we saw how if you take any of these alkylamines, they kind of have pKa's, they're conjugate acids, which are all around 10 to 11. So the pK of these ammoniamides for the alkylamines, all in the neighborhood of 10 to 11. But if we go over to this slide here, we have some arylamines. And you see that the arylamines have lower pKa's than the corresponding or similar alkyl ammonium ions. Well, why would that be? This is a stronger acid, let's say, than dimethylamine, which is a pK of around, where is it? Dimethylamine has a pK of around, its corresponding conjugate acid is a pK of around 11. Well, that means if this is a weaker acid, that means that this must be a stronger base. So it means that dimethylamine, if we just pencil it in here, so let me just write it like this. So we have dimethylamine. Okay, this, its corresponding conjugate acid is a pKa that's around, the pKa is around 11-ish. So that means weaker acid, and therefore this is a stronger base. Well, why would this in this circle be a stronger base than this? Well, remember that in order to be a base, a Lewis base is an electron donor. It's something that can donate a pair of electrons. If you look at the lone pair of electrons on dimethylamine, it's just sitting there, localized on the nitrogen. It's ready to act as a base, right? It's ready to donate the pair of electrons. Whereas if you look at the pair of electrons on the nitrogen of aniline, they're available, but not nearly as available. Why? Because you can draw resonance structures that shows their delocalization throughout the ring. Weaker base gives you a stronger conjugate acid. Give me a thumbs up if you just follow me on the concept. I'm trying not to over-explain it, but I want to make sure that I cover the details. I mean, this really goes back to your Gen Chem days and Organic 1 days when we said strong base, weak conjugate acid, strong acid, weak conjugate, et cetera, et cetera. So you're probably all fully aware of that. One more example. I can't help myself. Let's just do one more example here. If we compare the pKa's of the ammonium ions of Pyrrole and pyridine, you see that there's a huge difference in the pKa's of their ammonium ions. You see the pyridinium is a pK of 5.3, whereas the conjugate acid of Pyrrole has a much lower pKa. Why is that so acidic? If this is a stronger acid, let's go through the rationale again. Stronger acid, that means that this is a weaker base. Weaker base, and it means that pyridine would be a stronger base. And I'm just comparing these two, okay? Just comparing these two bases. Why is Pyrrole a weaker base? Could anybody give me a reason why? Doesn't have to be a super involved answer. What happens to Pyrrole when you form the conjugate acid? When you go from here to here, you go from something that's aromatic to something that's non-aromatic. So you lose the aromaticity. Whereas when you go and you protonate pyridine, you go from something that's aromatic to still being aromatic, right? So that is why Pyrrole is so much weaker as a base than pyridine. It's because once it gets protonated, you've destroyed the aromaticity. So this is one, I'm going to put a star by this one. I think this is worth knowing and just kind of having in your hat as you move forward in the class. In general, if you have an amine with more than 5 carbons, they're going to be slightly soluble in water. Solubility will be enhanced by the presence of aqueous acid. Why? Because a protonated ammonium ion is a cation, and therefore it's going to be water soluble. And that enables us to extract amines from organic impurities using an aqueous acid. Let's think about that for a second. Let's imagine you have a mixture of something like, let's pick diethylamine. So let's say you have diethylamine. Okay, so let's draw diethylamine, which is this compound. You can draw it a little neater than that, maybe. So if we have diethylamine, okay, and let's say you have that mixed with, I don't know, let's just pick an organic compound. Let's say you have, I don't know, just some kind of ester. Let's draw ethyl benzoate. Okay, so let's say you have some ethyl benzoate and you have dimethylamine mixed with it. Well, if you subject both of those to HCl, just a little bit of aqueous HCl, so let's just leave it like that, okay? Let's say it's just 1 molar HCl. The HCl is not going to affect this in any way at all. It's not going to change that whatsoever. So you're still going to have the ethyl benzoate, but it's going to affect this. What you're going to end up doing is protonating that. So you're going to end up protonating this to form its conjugate acid, like this. Plus, you're going to have the chloride ion, okay? And then you're just going to have the ethyl benzoate. I'll just draw it a little bit different this time. You're going to have the ethyl benzoate unchanged. So look what you've done. You've taken this and you've converted it to a salt. So now this is a salt, and that means it is water, here H2O, soluble. So if you put that in a separatory funnel or a vial or something, so let's imagine you have a conical vial and you shake it up, you're going to have two phases. Let's say your organic phase is on the top. That would have your ester in it. Your ester would be in here, but your amine would be in the aqueous phase as a salt. And so that is just an easy way to separate an amine from an organic compound. You just make the corresponding ammonium ion, which is water soluble. A very powerful technique extraction is in organic chemistry. Going back to that whole idea of amines containing nitrogens in them, I have a few different marketed compounds here. They have nitrogens in them, and I'm showing you how that they are marketed actually as salts. For example, if you look at Viagra, which is shown down here, so Viagra is actually marketed as a salt. Okay, so they market that as a salt. I don't know if you've ever heard of Gleevec before, but that used to be a really common drug for the treatment of leukemia. And then we have another hypertension drug over here, but these are all marketed as salts. So it's very important that an organic chemist understand how to make a salt from an amine and to understand basicity and acidity and those kinds of things to enable us to manipulate basic compounds and get them to do what we want them to do as chemists. The pKa of most alkylamine conjugate acids is between 10 and 11. We saw that earlier on, but we saw that an alkylamine had its conjugate acid had a pK of around 5. And again, this is just rehashing that concept, which is something I covered earlier. We said, why is it that the lone pair on trimethylamine, for example, is so much more available to be protonated? Why is its conjugate acid a weaker acid? It's because this is a stronger base. Why is it a stronger base? Because the lone pair is just sitting there. It has nowhere to go. Whereas if you take aniline, for example, so this is aniline, we can draw 4 resonance structures that show the delocalization of the negative charge or that lone pair throughout the ring. And if it's delocalized, it is what? This is the best way of describing it. It's less available for protonation. It's kind of like catch me if you can, you know? It's kind of like running around the ring trying to get away from the proton source. Anyhow, that's the way I imagine it. Now, what else is neat is that you can affect or adjust the basicity of an aniline by adding an electron donating group or an electron withdrawing group. Now, if you look at a nitrile, and we looked at this earlier on, a nitrile is a strong electron withdrawing group. So if you have an electron withdrawing group, that means it's pulling the electrons in this direction. That means they're less available. So that means that this is a very, very weak base. So weak base, okay? So that means it's going to have a strong conjugate acid. And if you compare the pKa of this conjugate acid to this one, we see there's a dramatic effect. Why is it? Because here where we have a methoxy group is an electron donating group, right? It can donate electrons through resonance. I'll spare you the whole, me drawing everything. So I won't do that right now, but this is an electron donating group. That means that this lone pair is more available. It's a stronger base, and therefore its conjugate is a weaker acid. So let's pencil that in here. So this is going to be a stronger base. We'll put in here weaker, put in here weaker acid, and we'll put down here strong, Anyhow, we have a stronger acid down here. I told you that I would come back to the basicity of an amine and why the lone pair on an amide is not considered to be nucleophilic or basic, and it is because it participates in resonance. You can see that it's adjacent to a p orbital. We have a p orbital here and a p orbital here to make our pi bond. Therefore, it can participate in resonance. You see the two contributors to the resonance hybrid of the amide right here. In fact, if you look at the electrostatic potential map of the amide, you see that most of the negative electron density resides on that oxygen. So again, we have a lot of double bond character, and so the nitrogen of an amide is actually sp2 hybridized. So let's scribble that in here. So this is sp2 hybridized, and that is why the lone pair of an amide is not considered to be a good nucleophile or a good base. Now let's talk about how amines exist at physiological pH. Physiological pH is around 7.3. It says here that amines at physiological pH actually exist primarily as ammonium ions. So if you ingest an amine, your chances are your body is just going to protonate it and form the conjugate acid of it. The ammonium ion will predominate at physiological pH. Well, why would that be? Well, the reason why can be justified by looking at the Henderson-Hasselbalch equation. If we think about physiological pH, which is around 7.3, and if we think of the pKa of an ammonium ion, which we said for an alkyl ammonium ion was around, let's say, 10 to 11. Let's just pick 11 as a pKa. Well, that means you have to have plus the log of something over something, the conjugate base over the acid. Well, in order for this to equal 7.3, you have to have 11 plus a negative number. How do you get a negative number? You have to take the log of a number that is a fraction. Okay, you're going to have to take the log of something that's less than 1. So let's imagine we just put in the number, 1 over 2. So if you take 0.5 and you take the log of it, you get negative 0.3. But the idea is that you've got to have something where you've got less of the conjugate base than you do the acid. So based on the Henderson-Hasselbalch equation, in order for this to be a negative number, you've got to have mostly this. You have to have mostly the conjugate acid, mostly ammonium ion, and you have to have less of the conjugate base. Give me a thumbs up if you follow me on that. I would say that's important for biochem moving forward. I know you probably don't want to think about Henderson-Hasselbalch equation. You're like, Mr. Dion, my Gen Chem 2 days are over, and that's totally fine. But it's something I want you to be aware of. I'd like you to be able to say, Mr. Dion did tell me that. And if you forget it when you get into biochem, just come see me in my office, and we can have a frank and early discussion about it. That's enough talking. Let's try some practice problems. See if we can solve a few problems. It says in 22.4, rank this group of compounds in order of increasing boiling point. So we'll call this one A, this one B, this one C. Could anybody tell me which one of these would have the highest boiling point, A, B, or C? And it's not a trick question. I'm sure somebody knows. Could anybody suggest which one of these would have the highest boiling point? Yeah. Absolutely. So one of my students says it's going to be B, right? And the reason why is this one's going to have the highest boiling point is because it's a primary amine. So we'll put here primary amine. They all have pretty close to the same molar mass. So primary amine, this is going to have highest boiling point. And then the tertiary amine is going to have the lowest boiling point. So tertiary amine, no opportunity for hydrogen bonding there. So this will have the lowest boiling point, and then C will be somewhere in the middle. Let's try 22.5. What was the rule of thumb? We said when we had a compound that was an amine that had less than four carbons or less, we said it would be water soluble. What about this compound here, A? Do you think that would be water soluble, yes or no? Could anybody answer that one? Just give me a thumbs up or a thumbs down, or a yes or no. You think that would be water soluble?
No.
I agree with you. That doesn't look water soluble to me. That's got a whole holy host of 8 carbons in it and only 1 nitrogen. Lindsay, I'm just going to put a big old no for that one. Lindsay or anybody, yeah, I agree with you, Nick. You too, Nick. What about B? Anybody have a thought about B?
Yes?
I agree with you again. Yes, absolutely. Yes. So this is isopropylamine. That's definitely water soluble. It's only got 3 carbons. And then this one here, it's got 6 carbons, but you've got 2 amino groups. So it's kind of a ratio of 1 to 3, right? If you split it in half, you know. So I'd say that this one would also be water soluble since it's a diamine. I find that students usually do really well in these questions. So let's move on to something that I think is a little more complex. It just says here, for each of the following pairs of compounds, identify which is a stronger base. So we're looking for the stronger base. What is the stronger base going to mean? It means lone pairs are available, the most available. Okay, you want the lone pair to be like, I'm ready, I am available to do something. So we're looking for the most available lone pair. Is it going to be the lone pair in red or the lone pair in blue? Could anybody tell me which one of these lone pairs do you think is the most available to just be protonated? Let's say you subject these to an acid. Which one would be protonated first, the red lone pair or the blue one? I agree, Karen. Right? It's not an easy question, is it? But it would be the red one. So we'll say, let's just write stronger base. Why is the blue lone pair a weaker base? It's because it can participate in resonance, right? We can draw a resonance structure for this. I mean, we could just pencil it in here very quickly. Let me grab the black pen. So we can draw this resonance contributor like this. Okay, so you can see that lone pair is not as available. It's delocalized throughout the molecule. The next one I think is a little bit, well, maybe not tricky, but come on, you. Don't zoom out that far. Let's try if we have the red pair and the blue pair. I've never tried this color coding the pairs of electrons. But what I want you to remember is that Pyrrole is going to be a very weak base. Right? Why is Pyrrole such a weak base? Because if you protonate it, you break the aromaticity. Okay, Pyrrole is aromatic. Okay, this is an aromatic compound. If you take Pyrrole and you protonate it, so let me just I'll slap a proton on here, then it becomes non-aromatic. The molecule does not want to do that. It hates doing that. Whereas if we look at the other molecule here, this compound is already non-aromatic. Okay, this has got nothing to do with an aromatic ring, because if this was in a p orbital, then you'd have an anti-aromatic compound. So it's non-aromatic compound. This nitrogen is sp3 hybridized. This lone pair is just sitting there. Okay, it is just ready to be protonated, and thus this will be the stronger base. So that's based on aromaticity. That one's kind of tricky, I think. What about C? Let's try it again. If I put in this one's got deleted. If I put in a lone pair here in red and a lone pair here in blue, could anybody tell me which one of these would be the stronger base? Would it be the red lone pair or the blue lone pair? Which one would be a stronger base? Exactly. Yep, 100% correct. Okay, all of my students are right. Karen and Nick both said it's the red ones, and they're both right. So let's pencil that in here. Stronger base. Why? Because again, these ones are delocalized throughout the molecule. I'm not going to draw the resonance structure, but yeah. And then D is in the same vein as B, right? If you look at the lone pair on this molecule, so this is called indole. It's called indole. You don't need to know that. But this lone pair is participating in aromaticity. Okay, so you need to have that lone pair. If that gets protonated, so I didn't mean to erase that. If you were to protonate this, then you end up with something that's non-aromatic. But when it's not protonated, it's aromatic. Okay, so this is an aromatic ring, whereas this nitrogen is already sp2 hybridized And so the lone pair resides in an sp2 hybridized orbital. It is localized. It's just sitting there. So that means that this one is going to be the stronger base. Any questions about that? I don't think this is easy. I don't think, or I mean, everything that we do is doable, but I think this is challenging. So the fact that you're able to answer these questions, I think, is a very good thing. Not simple. You know, looking at it and saying this is a strong base. Any questions at all? And again, as always, never hesitate to interrupt me. It's not even interrupting. It's what we're here for. If you want to ask a question, you go ahead and do it. Let's try a couple more slides, and then maybe we'll take another break here. But let's take a look. This one's a little more challenging, I think, if we look at these compounds increase in terms of increasing basicity. So I'll put a blue pair here, put a red pair on here, and then why don't we put a black pair of electrons over here. You know, the first thing you really got to do is just look, you know, what do these molecules all have in common? They all have this in them, right? They all have this portion, you know, that's in common between all of them. So really, all you need to do is kind of look at the groups that are attached here. And if we look at the bromine and the aldehyde, I mean, these are electron withdrawing groups. This is an electron withdrawing group. This is an electron withdrawing group. Whereas a methyl group, hey, that's not electron withdrawing, that's electron donating by a hyperconjugation. It's not strongly donating, but it's an electron donating group. And so based off of that, which one of these do you think would be the strongest base? The one with the blue pair, the red pair, or the black pair? So we're talking about the strongest base. Go ahead, Lindsay.
Is it the black?
Yeah, it's going to be the black ones because the black ones have electron density being donated towards it, right? So it means they're going to be super available to go out and protonate something. Whereas the red one, let me just grab this, you're going to have dipoles pulling this way, so it yanks the electrons away. And you could also draw resonance structures, right? You could draw a resonance structure. You show this thing all the way down to here if you wanted to. You could show it delocalized there. So this one would be the strongest base. Strongest base. And then this one would be the weakest base. Again, not a simple question. Fun question, but not a simple question. You know, I ran into one of my friends in Montreal the other day, and he whipped out his favorite saying, you know, if it was easy, anybody off the street would be able to do it. Let's talk about a couple of ways to make amines before we take another break. I just want to show you a couple of quick things here that I think you'll find interesting. There's one new set of conditions in here that I just wanted to expose you to before we take a break. So we've actually already looked at a couple of ways to make amines. I mean, we're pretty far into the class at this point. And do you remember learning how to make a primary amine by the reduction of a nitrile? Like this goes all the way back to Organic Chemistry 1. I mean, this is something that I covered in Chapter 7 of Organic Chemistry 1 when we discussed SN2. You know, you add a nitrile, you expand the carbon skeleton by one carbon, and then you can take that nitrile and just treat it with excess lithium aluminum hydride followed by water, and that just reduces that all the way down to a primary amine. But again, you see that here you have 1, 2, 3, 4, 5 carbons, and here you have 1, 2, 3, 4, 5, 6 carbons. So you do add a carbon to the skeleton, but hey, it is a way to make a primary amine. So we saw that earlier on. Another way that we saw was a reduction of a amide, and this is one of those things that there's no mechanism for this in our textbook at all. This is something that was in the carboxylic acids chapter, taking a primary amide and then reducing it with lithium aluminum hydride followed by water. Well, how do you make a primary amide? You can make it from an acid chloride, take the carboxylic acid, treat it with SOCl2 or thionyl chloride, then excess ammonia. That makes the primary amide, and then we reduce that. Notice that the second step is water, right? The second step was water there. The second step is water here. It can't be acid, so we'll put here not H3O plus in this case. H3O plus, because if you did that, then you'd end up with this. Okay, you'd end up with the ammonium ion. You don't want that. So that's another thing that we saw. And then this slide has something that's a little nuanced. Let me show you quickly what it is. And you might have your eye drawn to it already. You remember nitration of an aromatic ring using nitric acid and sulfuric acid? We made the nitronium ion. Remember that? I taught you all about the nitronium. And it was a super powerful electrophile, and the aromatic ring came out and you made the sigma complex and blah, 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 and then you made nitrobenzene. Okay, well, we said that you can reduce nitro groups with hydrogen, palladium, platinum, or nickel. But then we also said you can use a whole holy host of metals like iron, zinc, tin, in acid. And what that will actually give you first is the aniline. So it gives you this compound, NH3 plus, and then you have to treat it with sodium hydroxide, right? In the second step to make the aniline. But this is something new. So let's put where's my blue pen? Put a circle around this. This is tin 2 chloride. Tin 2 chloride. In tin 2 chloride, the reason that we have tin 2 chloride in there, I don't really have anything in there. It's because tin 2 chloride is like a really mild reducing agent, and it can come in handy if you have something that could undergo hydrogenation or reduction. It just works as really good conditions. Like an example would be, I'm not going to write this down, but let's say you had an aldehyde in the molecule. Aldehydes might react with these conditions. They could cause it to be reduced. And so that's when you would use the tin 2 chloride. I'm not going to quiz you on that. I might put a question in the homework when you could go back and look at the book, but I wouldn't ask you specifically, like, why do you need tin 2 chloride in this specific example on a quiz, okay? But we'll write it down here. Why don't we write down here? New mild conditions. New mild conditions. Okay, great conditions, just very mild way of doing a reduction. Well, let's see here. It says draw the structure, alkyl halide or a carboxylic acid that might serve as a precursor for the preparation of each of the following amines. Well, we could come up with a carboxylic acid or an alkyl halide for either one of them, really. Why don't we do alkyl halide first, and then we could do a carboxylic acid second? Why don't we start with 22.10A? So we'll start with this guy right here. If we wanted to use an alkyl halide, well, then we would use sodium cyanide. But sodium cyanide means we're going to add this carbon to the molecule. There's my pen there. So that means you would only need a propyl group. So to use a cyanide, you would just use propyl, iodide, bromide, or chloride. Then in the first step, you treat that with sodium cyanide. Maybe I'll just draw the whole thing out here. So you treat it with sodium cyanide. It's just a little SN2 reaction. Then you'd have this. You'd have the nitrile here. Then you would treat it with LaH, followed by water. And that's going to give you the primary amine. So 1, 2, 3, 4, and the primary amine. If you wanted to make it from the carboxylic acid, you'd want to make it from the amide. So you'd start with butyric acid. Let's write out the structure of butyric acid. Excuse me. And we actually saw this a few minutes ago. Oops, there we go. That's better. First step is to treat that with thionyl chloride to make the acid chloride. Then we're going to treat it with excess ammonia. That's going to make the primary amide. So 1, 2, 3, 4. We get the primary amide. And then we just do the reduction, right? The reduction of a primary amide. First step is lithium aluminum hydride. And second step is water, of course. And that's going to give us the same old 1-butanamine. Or you could call it butylamine. Either one would be perfectly fine. I don't think we only need to do one more of these. Why don't we take a break And everybody could just give 22.10 a quick go, and then we'll come back after a short break and we'll try that one. And then we're going to get into section 22.5, which deals with ways, some new ways to prepare amines. And what I really wanted to get into with you today was azide synthesis. We'll cover that, but there's a reaction I want to show you, not Gabriel synthesis. That's cool too. Yeah, I wanted to at least mention this with you today. This is a really cool reaction, reductive amination. So when we come back after the break, we'll see if we can make it all the way to discussing a little bit about reductive amination. Very, very cool chemistry, very neat chemistry. So let's go back here, and everybody will give this question. Where the heck was it? Right here, 22.10b. We'll all give that a shot. So what time is it now? Let's see here. It is currently 3:31. Why don't we come back at 3:45? We'll come back at 3:45 p.m. and we'll give this one a shot, and then we'll get into some even more exciting reactions. All right. So I'm going to leave this up so you guys can see it, but we'll come back at 3:45.